Okay, now we want to look at the intersection of lines in space. How do lines intersect? And if they do intersect, how do we describe the intersection of a line? Well, there are a number of scenarios that you have to get. Let's say you have two lines, L1 and L2 here. So I want to kind of discuss the interactions of these lines. Do they intersect or not? Are they parallel to each other or not? If they are not parallel, then do they intersect at all? If they do not intersect, then yeah, they do not intersect. If they are parallel and they intersect, are they different lines, or maybe they're even just the same line? Now, to do that, let's look at the cases which are possible. In the first case, what is happening? Well, there's a likelihood that the two lines are, one line is here and one line is this one. This is our line 1 and this is our line 2. The two lines are clearly different, and they intersect at only one point. So this is the first possibility. The lines are different, meaning they are distinct, and they intersect at exactly one point. So that is one possibility. Well, in the second case, it is possible that the lines are parallel to each other and they coincide everywhere. So it's like I have one line, is this one, and then I have a second line. For the second line, let's go a little bit more. Something like this. Now, clearly here, you can tell that if this line were to be somewhere like that, of course, not perfect. Can I tilt it? Okay, better. If you look at it like this, our two lines, one, let's say this is line 2, and then we have the other one inside, that is line 1. In this case, you see that the two lines are literally one and the same line. They have the same direction. They have everything almost the same. In this case, we see to say these two lines, they're not distinct. It's the same line. We can say it's just one line. Or we can say that our two lines, L1 and L2, we can argue to say that they coincide everywhere. So they coincide at all points. So we can say they are coinciding lines, or saying that they coincide everywhere. Let's say they intersect at infinite points. Infinite number of times, number of points. What this means is these lines will intersect literally everywhere. They intersect here, they intersect here, they intersect here. Everywhere they will intersect. One, observe that the two lines, for this to be possible, first, the two lines must be parallel. So for this to be possible, the two lines must be parallel. Apart from being parallel, what else do we see? They must have the same direction vector. So these two lines must have the same vector v. So their direction vector must be the same. And then what else? You see, any point you pick must also be true, must also lie on the other line. So if I picked a point, maybe 1, 2, 3, that is on line 1. That point must also lie on line 2, since they intersect everywhere. This is the second case. In the third case, you see, it is possible that the two lines are parallel to each other, but they do not intersect at all. So what happens in this case? Well, if the two lines are parallel, but they do not intersect, what does it mean? Well, the key difference between this version and the previous one is that even though they are parallel, or for them to be parallel, what this of course implies is if they are parallel, then it means that their vectors must be the same. So the direction vector from line 1 must be the same as the direction vector from line 2. This comes from the fact that they are parallel. But because they are different, it implies that they do not intersect, not even once. So the thing about parallel lines is either they intersect everywhere or they do not intersect at all. That is the whole thing about parallel lines. It's not possible for us to move line 1 so that it gets to intersect with line 2 only once if they are parallel. Notice that the minute it intersects with line 2, even just at a single point, it intersects with line 2 everywhere else. So if two lines are parallel, either they intersect everywhere or they do not intersect at all. So that is the thing with lines which are parallel. Okay. Okay, so that is if they're parallel. Now, let's look at the fourth case. In the fourth case, what is happening? Well, in the fourth case, we have lines that can be different, but still not parallel. So you can have one line that is going like this, and then you have a line that is below it. So I can say this line is below that one, and these two lines are not intersecting. One line lies on top of the other. So of course, this is too deep. Perhaps this is why this might almost seem like they're intersecting, but we have one line on top of the other. So these two lines, L1 and L2, are different, and they do not intersect. Such lines are said to be skew lines. So if lines are said to be skew lines, they are just saying that they are not parallel and they do not intersect at all. Are we okay there? So those are the four cases that we have to look at. Let's look at a few examples. So what is the question? Discuss the intersection of the following lines. In this example, we have lines, and then we're being asked to discuss how these lines intersect. So we have those two lines given, and you can tell that the two lines are given in vector form. So the first thing, the last one here, I didn't write it well. So that is -1, sorry, I wrote -2 again. This is -1. So when you observe these two lines, the first question you want to answer is, are they parallel to each other? That's the starting point. Are the two lines parallel? So what is the condition that is necessary for two lines to be parallel? What did we say? If two lines are parallel, what does it mean?
They have the same direction vector.
They have the same direction vector. So look at our two lines, L1 and L2 here. Do they have the same direction vector?
Yes.
Yes, they do. So all you had to look at is this part here. This is where the direction vector is. So this part is the same. So I have a tendency of writing my S and my 5 literally the same way. So to avoid that, let me use the parameter N instead of S for the second line. So clearly in this case, we can tell that the two lines are parallel to each other. But if they are parallel, then we know to say they are either this case, which case is that? This case where they are parallel and they are exact, as in same line, or they are parallel but they are different. So then it means this case. The question is, how do we tell which case we are dealing with? So in this case, what we have to do here is, you see, for two lines to be parallel, it means that, like I mentioned, either they intersect everywhere or they do not intersect at all. So what we'd have to do here is pick a point that is known to lie on one line and then check if it also lies on the second line. What do I mean? Can you identify one point here that lies on line 1? Identify a point that lies on any line here. Let's say line 1. So remember how we represented these lines. They were made of two things, the direction of the line and the point on the line. The point on the line is this part here. This is a point on line 1, and this is a point on line 2. I hope you guys remember that. So when I was asking to say that, can you identify a point that lies on line 1? Our point on line 1 can be taken as 5, 11, 2. This is a point that lies on line 1. So that part is justified. Now, the next thing that we want to do is want to pick this point and ask ourselves, will it satisfy line 2 as well? Will it lie on line 2 as well? What do I mean? We'll come to line 2 now, and we'll make the parametric equations of line 2. So get line 2 and we'll make the parametric equations there. We're going to have x is equal to 1. Then this is going to be plus n. Then we're going to have y is equals to minus 9. Then we'll have plus, that's minus, plus, yes, 5n. And then the last one is going to be z is equals to 9. And then this is going to be minus z. So these are the parametric equations from line 2. Now, when I say, does this point satisfy line 2 as well? You see, this point gives us the values of x, y, and z. So what we'll do is we'll substitute the responding values in the symmetric equations. And what, this is not z, this is n. For this point to lie on line 2 as well, it means that when I get this point and plug 5 where there is x, and work this one out for n, we get n is equals to 4. See, the values of n I'll get from each parametric equation here, they must all be 4. They must be the same, because here, for any point that we pick on this line, the value of n must be the same throughout. Have you guys got that?
Yes.
So when I substitute the other values, 11 where there is y, 2 where there is z, if I get the values of n to be the same, then my conclusion will be that, yes, the point we picked from line 1 also lies on line 2, so the two lines are parallel and they coincide. But if even just one of these values of n was going to be different or is going to be different, let's say I find this one to be maybe a 3 and not a 4. Just from this realization, we will conclude that the two lines are parallel, yes, but they do not intersect anywhere. Just because this single point failed to intersect with our line, it implies that no point will intersect with the other line as well. Is that clear? So we have found for the first one, we found n is equals to 4. Let's try for the second one, what we get here. So we plug in 5, not 5, this is now 11, where we have y. This is minus 9, and then plus 5n. What does this imply? The 9 goes the other side, it's now plus 9, that is 20. Then 20 divided by 5, we get 4. n is equals to 4. This is looking good so far. Maybe they are the same. Maybe this is going to give us n is equals to 4 as the last one as well. Let's try it. So we now plug in 2 where there is z. So if we plug in 2 where there is z, we now have 2 here is equals to 9 minus n. Let's see what we get. The minus n goes to the left, the 2 goes to the right. We're going to end up with n is equals to 9 minus 2. Well, 9 minus 2 is not 4. 9 minus 2 gives us 7. And when you look at this clearly, what does that mean? Do our two lines intersect, or do our two lines not intersect?
They don't intersect.
They don't intersect. So how do we conclude? Since our point, that's 5, 11, 2, it lies on line 1, but it does not lie on line 2. What does that mean? Then L1 and L2, they do not share any points at all. So we say they are parallel, They are parallel. We saw that earlier. They are parallel and distinct. By distinct just mean different. So we can say they are parallel and distinct, or they are parallel and they do not intersect anywhere at all. So this is how we discuss the intersection of two lines if they are parallel, and we want to see if they intersect or they do not intersect. Let's look at a second example. In the second example, what is happening? Well, in the second example now, let's pick a line. Same question. We want to discuss the intersection of these two lines. So when you look at this, are you able to conclude whether they intersect or they do not intersect?
We can only conclude that they're not parallel.
We can only conclude that they are not parallel. Yes. Yeah. And how did you conclude that these two lines are not parallel?
The direction vectors in the denominator are different.
Yes, the direction vectors. And as we saw earlier, the direction vectors for symmetric equations is going to come from the denominator there. So these are different. The red are for line 1, and for line 2, the direction vectors are given by this. So clearly they are different. This implies that the two lines are not parallel. Now, since they're not parallel, the next question is, well, then what do we have? Are they not parallel but skew lines such that they do not intersect at all as well? Or maybe they are not parallel but they intersect. How do we show that? How do we answer that question? Well, to do that, the first thing you'd have to do is to write each line in vector form. Ideally, we want to get the symmetric, not necessarily vector form. We actually want to get the symmetric equations of each line. So how do we do that? Are you guys comfortable moving from symmetric to parametric? Want to get the parametric equations. These are symmetric. Want to get the parametric equations of each line. So how do you want to change this? From parametric to vector first, as in from symmetric to vector first, or from symmetric to parametric? Which one are you comfortable with? So if we wanted to reverse from symmetric to parametric, how would we do it? Well, let's pick line 1, for example. So to reverse line 1 from symmetric to parametric, choose the parameter here. We can use t. We've been using t for some time. Let's use t. So the idea here is that this has to be equal to t, this has to be equal to t, and so does that. So we have t is equal to x minus 2 over minus 5. So that in the end, we have minus 5t is equals to x minus 2. Then make x the subject. The minus 2 goes to the left, it becomes positive. I'll start with x. So this is x is equals to 2 minus 5t. That is a parametric equation, the first one. We now just have to do the same thing for the other points as well. So see what I did? I equated t to this, or I equate t to that over 1. I cross multiply so that I get 1t equals to y minus 1. I make y subject and start with y. Y becomes equals to 1, positive 1, then plus y. That becomes the parametric equation, for y. I wrote y there, t is t. Now, for the last one, we'll try to be a little bit quick about it. We know this has to be z, but z is equals to, the first one will have to be this one here, but it changes sign. So if that is a negative 3, it's going to be a positive 3. Then it's going to be the variable with the parameter, our parameter is t, but the t will get this with its sign. That is positive 4. So this is going to be plus 4t. Observe that it's the same thing which was happening here. I was writing for y, so this is basically just y. And then this is minus 1, so I'll take it as positive 1. And then this is t multiplying the parameter down here, the number down here with its sign. So it's t times 1, which is just t. So here, this is how you go about it if you wanted to take a shortcut. So these become the parametric equations for line 1. Let's do the same thing for line 2. For line 2, we'll use a shortcut now. The parameter we'll use here is going to be n. So this is going to be x is equal to, can you predict how this will go? By shorthand?
Positive 3 plus 4n.
Positive 3 or negative?
Yes.
Hold on. What did you say? Is it plus 3 or negative 3?
Negative.
Negative 3. And then plus 4n. The next one is going to be y is equals to?
See, positive 2 minus n.
Minus n, yes. And the last one?
Positive 7 plus 6n.
Yes. So we have written down the parametric equations of each line. Now, the difference between this one and the previous part, because you might think, say, why don't we just pick a point on line 1 and plug it into line 2 and see if it gives us the same value of n there? Well, the difference here is that the two lines are different. So if we pick 1 point on line 1, we can't expect it to lie on line 2 as well, because if they are different but they still intersect, it would mean that they probably just intersect at 1 point. What if the point you have picked is somewhere way off, somewhere there? Obviously, it won't give us the same values of n because it's somewhere else there. The only point that would give us the same values of n would have to be a point which is exact and somewhere there. So because of that, we cannot use that method in this case. It would throw us off. So instead of that, how do we do this? Well, we want to find the value of t and the value of n, which ensures intersection. We're not sure if they will intersect, so we'll have to test it later on. How are we going to do that? Well, picture this. See, each equation here, these are equations of x, and these are equations of y, and these are equations of z. So what we'll do is that we'll pair them up. From the first pair in terms of x, we have 2 minus 5t is equals to minus 3 plus 4n. What we're doing here is we're trying to solve for n and t, which would give us intersection. Then we'll see if it actually does give us intersection for us to make a conclusion. From this expression, we can easily simplify. And what we're going to get is, this is going to be 2 plus 3 is equals to 4n plus 5t. So in the end, we can say we have 4n plus 5t is equals to 5. This becomes the first equation. The next one is going to come from y. When we do the same thing for y, we have 1 plus t is equals to 2 minus n. From here as well, we're going to have t plus n. The 1 goes to the right side, it becomes negative, so we end up with 1 here. This becomes the second equation. And from the z expressions, what do we see? From the z expressions, we have 3 plus 4t is equals to 7 plus 6n. From here, we can group them as well. We end up with 4t minus 6n On the right side, the 3 goes there, becomes negative, so we get 4 there. This is the fourth one, the third one, I mean. Now, I'll hold on to this one. See, to find n and t, you don't need all 3 equations. You just need 2. So what we'll do is that we'll solve the first equation and the second equation to find what n and t is. Now, if they intersect, it would imply that the same 2 values of n and t must satisfy equation 3 as well. Meaning that when I plug in what t is and what n is, when I plug them there, they should reduce to give me 4. If they do that, I will conclude that yes, my 2 lines intersect. If when I plug them here, they fail to give me 4, then it would mean that my 2 lines do not intersect and those 2 values of n and t never really match at any point. So that is going to be the success criteria of this check. So let's first find n and t using the first 2 equations. From the second equation, I'll make t subject. We end up with 1 minus n. And when I plug it into the first one, I will have 4n plus 5. Where there's t, we have 1 minus n is equals to 5. Simplify this, 4n is equals to 5. From here, 4n minus 5n, we get minus n. Then the 5 goes to the right, we have 5 minus 5, which is 0. This is telling us that n is equals to 0. Now, from the second equation, which is this one there, we did end up with t being equals to 1 minus n. But because n has turned out to be 0, t just ends up being 1. So we now have expressions for n and t. But do these values of n and t really exist? If they do exist, then they must satisfy the third equation there as well. So from the third equation, we can say we have the left-hand side, which is 4t minus 6n, and we have the right-hand side, which is 4. So what I want to see here is, when I get the left-hand side, and where there's t, I put 1. Where there's n, I put 0. Will I get the right-hand side? Well, it turns out we do get the right-hand side, 4, which is the same as the right-hand side. So in this case, we conclude that yes, the 2 lines intersect. We saw they were not parallel, but here we have just concluded that the 2 lines intersect. So based on this realization here, we conclude that L1 and L2 intersect. If they intersect, then we still have one question to answer. Where? Where do they intersect? To find the point of intersection, you don't need both n and t, you just need one of them. So just come back to these expressions, not the symmetric, the parametric equation. Just pick one, or pick this one here. Let's pick the one for n, which is simpler since n is 0. So regardless of the one you pick, you get the same results. So pick that for n. So pick that, and then what we do here is, where there's n, substitute the value of n. So we saw n is 0. So when you put 0 where there's n, this is going to be minus 3. This is going to be y is equals to 2. And this is going to be z is equals to 7. Having found those, then our conclusion can be complete. L1 and L2 intersect at, this is -3, 2, 7. You can even just throw in only to mean that they are not parallel, because if they are parallel, then they intersect there and perhaps everywhere else. So in this case, they intersect at only one point. Have we got that? Any questions so far? Okay, looks like we're okay with